All right, time to review some Unit 1 limits. So here we go. We've been learning about these limits and ways to find limits. So here we have a function. We want to find the limit as x goes to 0. Well, remember, we can always start by trying to plug it in. And if we can evaluate this by direct substitution, then we're good to go. And I think this does work. If we plug in 0, we get 0 squared plus 0 plus 20 all over 0 squared minus 16. Looks like negative 20/16. And that is what? 4 goes into those, so we got negative 5/4. Okay. All right, not too shabby. Well, what if we find the limit as x goes to 0? Well, as x goes to 0, these small things don't matter. All right. So 20, we got only the highest degree in the numerator and the highest degree in the denominator matter. So this is equivalent to the limit as x goes to infinity of f of x squared over x squared. And what's x squared over x squared? Well, that's just 1 over 1 or 1. All right, so this is going to 1. As x goes to 4, well, we have a problem. So our problem here is if you plug in 4, you get 0 here, and I'm pretty sure if you plug in 4 here, you're going to get 0. So we're going to take the limit of f of x, and we're going to rewrite the limit, and we're going to factor it. So the limit of that rational function is the same as, well, let's factor it up. The bottom factors into x minus 4 times x plus 4, and it looks like the top is x minus 4 times x plus 5. And so this limit is equal to this limit. That is a very true statement. We've got to keep our statements true. X minus 4 cancels, and so the limit of f of x is equal to the limit of this expression. And now 4 is not a problem, so we can plug in 4. And so this is equal to 4 plus 5 over 4 plus 4, which is 9/8. All right, there you have it. All right, so let's talk about discontinuities for this function here as we just kind of analyze this function up. So where are the problems? Well, the problems happen when x is 4. We kind of saw that. Now x minus 4, which causes the problem here, cancels. So that is a removable discontinuity at x equals 4. So 4 can be removed by canceling. However, this expression is equal to this expression, and negative 4 is still a problem. We don't do the limit for negative 4, but negative 4 is still a problem. So that is not removable. So, well, we're going to have an infinite asymptote. All right. And remember, an infinite asymptote, which is going to be, infinite discontinuity, which is a vertical asymptote. Okay, so we have a discontinuity, which is a vertical asymptote at x equals negative 4. Okay, so two types of discontinuities there in that function. So what's the horizontal asymptote? Well, the horizontal asymptote happens, remember, as x goes to infinity. So as x goes to infinity, we get a horizontal asymptote at 1. So as x goes to infinity or negative infinity, we've got to consider that as well. Negative infinity would be the same because this fraction goes to 1 no matter what. Then f of x goes to the line y equals 1. All right? Okay, let's look at a piecewise function here. So here we got a piecewise function, and this piecewise function might have some problems at these boundary points, or these points where it changes, all right, at 1 and 3 specifically. So let's investigate a little bit here. We want to find the limit as x goes to 1 of g of x. So remember, we got to look at this from both sides. So we need a limit as x goes to 1 from the negative side of g of x. Well, we're just going to plug that in. For x less than 1, that goes into here, and we can just plug in 1 there, so that's 2. And the limit as x goes to 1 from the positive side of g of x, well, that's going to be the second piece because x is bigger than 1 here, so we're coming up on this. And I think we can just plug it in. It looks good. 4 times 1 minus 8, all over 1 squared minus 1 minus 2. And that looks like, what do we got? Negative 4 over, that's negative 2, right? So negative 4 over negative 2. Watch out for your arithmetic. And that's going to be 2. Okay? So it's coming to 2 from both sides. 2 from the left, 2 from the right. That means we have a limit. Remember, to have a limit, a function limit, we need to have a left-hand limit and a right-hand limit that agree. Doesn't matter if the point itself is at 2, but they must agree from both sides. What about the 3 plus? We'll do the same thing here. All right, so we can find the limit as we go to 3. I'm sorry, this is not an overall limit. This is just asking for 3 plus. Okay, read carefully. So that little plus there, all right, over here, that little plus, right, just means we're coming from the right side. Which one of these is the right side? Well, this one is from the right side. Okay, so from the right side, we got natural log of 3 minus 3. Well, that's a problem. So natural log of 3 minus 3 is the natural log of 0, which is undefined. Okay, so what are we going to do? Well, we're going to have to think about what's happening here as we're really close. So we're going to have to pick something like a 3.1. Okay, that would be a log of 0.1. So if this is 3.1, all right, let's go back. That's the 3.1 minus 3. Well, that's going to be the log of 0.1. All right. So, well, the log of 0.1 is that a really big number or a really small number? Well, one way to remember that is to think about our natural log y equals natural log of x. Remember that graph? That graph looks like this. Okay, and this is 1. So when x in this function, when x is 0.1, it's going to be way down here, right? Okay, and if this is 0.01, it's going to be even farther down. So the natural log of x for very small numbers, just bigger than 0, are going to be very negative, all right, going down to negative infinity. So this one's actually going to negative infinity is where it's going, all right? So this is very small, okay? So it's going down to negative infinity as we pick something closer and closer to 3, all right? Not really any other fancy way to do that other than graphing, all right? But we need to be able to do this without graphing, so got to be careful with that one. How about g of x, the limit as x goes to 3? Well, this one's going down to negative infinity. As x goes to 3 here, well, I think it's defined. Let's just check that out. The limit as x goes to 3 negatives from the left side, I believe we're fine there. 4 times 3 minus 8. And if you plug in 3 on the bottom, 3 squared, which is 9, minus 3 minus 2. So on top, we get, let me just do this. I should have put g of x equals. There we go. So this is 4 on top. On bottom, that's what? 9 minus 3 is 6. Minus 2 is 4. So this is going to 1. All right, so it's actually defined from the left. All right, so the limit doesn't agree. One's going to infinity, one is going to 1. So the limit does not exist because they don't agree. Okay? From the left and from the right. So, how about the removable discontinuity here of this graph? Is there a hole somewhere? Well, the only place there might be a hole would be in the middle. So if we factor 4x minus 8 and x squared minus x minus 2, all right, let's see, does that factor nicely? I hope so. So this is 4 times x minus 2, and this would be x, what do we got, minus 3? No. How about x? Two numbers that add to 1 and multiply to -2. So that'd be -2, which is what we wanted. because the top factored, and x plus 1. There we go. Those multiply to -2 and add to -1, right? Cool. So yes, there is a whole or a removable discontinuity at x equals 2. Now, where exactly is that? Well, after we cancel this, we get 4 over x plus 1. And when we plug in 2 there, so that gives us 4 over 2 plus 1, which is 4/3. So at x equals 2, and y equals 4/3, or we could say at the point 2, comma, 4/3. Okay? All right, that's the idea. So here's an interesting one. We got a function that has some a's and some b's in here. If we know that this function has an infinite limit, a limit as we go to infinity of 5, well, that means that as x goes to infinity, this has to be 5. So we're saying the limit as x goes to infinity of this thing, ax minus 12 over 3x minus b. Well, let's kind of just work with this a little bit here. As x goes to infinity, these constants go away, right? So this is the limit as x goes to infinity, which is ax over 3x. And so that's just a over 3, right? Because those x's cancel. And at infinity, that is, right? And we're saying that equals 5. All right, well, take this little equation here, and let's multiply both sides by 3. So this implies that a equals 15. Make sense? Hope so. All right, what about if we know that the limit as x goes to 4 does not exist? All right, let's pick a different color. There we go. All right, well, so we're saying the limit as x goes to 4 of ax minus 12 all over 3x minus b does not exist. Well, we got to ask ourselves, what would cause a limit to not exist? And that would be if we have a horizontal asymptote. This is a rational function. And so if we have a horizontal asymptote or a non-removable, let's back up, vertical asymptote. Vertical asymptote, which means that the bottom goes to 0. So we need 3x minus b to be 0 when x is 4. All right, so that would give us a vertical asymptote. Okay, vertical asymptote. Well, let's solve that up. So we can plug in this 4 into there. So we have 3 times 4 minus b is 0. Well, you can kind of see what's going on there. 12 minus b equals 0, so 12 equals b, right? So if b is 12, then the bottom is 0, and, well, we'd also have to have an a so that we can factor that out. A would not be 1, but that's what would have to be the case there. All right? Cool. Well, let's go on to the next page here. Continue our little review. Here's another interesting one. Okay. We got a single function with these characteristics that we want to create a single function that has a removable discontinuity at x equals -3. Well, what does it mean to be removable? Okay, well, removable means it can be canceled out, right? So if x equals -3 is a removable problem, then that means x plus 3 has to be in the top and the bottom, right? Okay. If there's a non-removable discontinuity at x equals 2, that means there's a factor down here, x minus 2. Okay. So you can see that this is a quadratic on the bottom and a linear function on top. Okay. Now, just for kicks, Let's go a little, if you're watching this, here you go. Here's a little step further. What if we say this function has a horizontal asymptote at, let's say, 7/11ths. Slurpee time. Okay, 7/11ths. Well, what does that mean? Well, if this is a horizontal asymptote, we know that this whole thing has to have leading coefficients of 7/11ths, and it's got to have the same degree. Okay, so with this, so let's call this our little extension. Okay, just a little note. Okay, so there's a good answer for that one. That's fantastic. That's really all we should have for that one. Okay, but a little extension, a little bonus here for those that are watching this review. Okay, well, in that case, we'd have to have this. We'd have to have our x plus 3 and our x plus 3 that cancel. We got to have our x minus 2. But we need to make the top quadratic. How do we do that? Well, I don't know. You pick something. It could just be an x plus 1. I don't know. Now they're both quadratic. And but we'd have to have a leading coefficient. What's our leading coefficients? 7 and 11. All right. So that would be bonus round there, okay? That would be all of those top two and have a leading coefficient or a horizontal asymptote at 7/11ths. Okay, cool. Moving on here, let's find these limits algebraically or analytically is another way we say that, all right? So we need to kind of show those important steps as we do this, all right? So here we go. We can try plugging in 2, but if you plug in 2, you're going to get 0 over 0. So don't put 0 over 0, okay? That is not the limit. And don't say it's undefined because of 0 over 0, right? That's the whole point of using our algebra. All right, we can use our algebra to hopefully remove the problem. And so the top here is x plus 2 times x minus 2. And the bottom is x, let's see, plus 2 and x minus 6, I think. Actually, nope, sorry, it's minus 2. Just check that. Minus 2 and positive 6, right? Because we need to positive 4 here in the middle. All right, that means the minus 2's cancel. Okay, and we're looking for the limit as x goes to 2. So it's good that those x minus 2's cancel. And so this is just going to be x plus 2 over x plus 6, which we can substitute 2 plus 2 over 2 plus 6, which is 4 over 8. Okay, this is, I know, is good. It's simple. You might say, do I really need to write that? It's a good idea because this is proving where this comes from. Okay, this doesn't come from 1 plus 3, doesn't come from a half times 8 or anything like that. It comes from the 2 you substituted plus the 2. So that just justifies it even better. So good habit there. All right, what about this one? Well, factoring is not going to work for us here. So we need to multiply by the conjugate. So we're going to multiply by the conjugate to move this radical. If the radical's on top, we do the same thing. So what's the conjugate here? Well, this is 3 minus, so we're going to have 3 plus the square root. Be careful. Don't go changing this minus. This minus is not part of the conjugate there. Leave that square root alone. Whatever's in there, leave it alone. We're changing the minus in between these two terms to a positive. And we know what you multiply the bottom by, you got to multiply the top by. Same thing, because we're really just multiplying by 1, right? When you multiply by 1, it doesn't change anything. Okay, so what happens? Well, on the top, we don't want to do anything. X plus 4, just leave it alone. Because our whole goal here is to cancel out that x plus 4. We're hoping that works. Let's see if it does. So the bottom, this is an a minus b and an a plus b. Do you remember what a minus b times a plus b is? Well, it's going to be the first thing squared, a squared minus b squared. First thing squared is 9, and the second thing squared is this square root that's squared. Okay, but is this okay, what I'm writing? Not quite right. You got to have those parentheses. If you don't have those parentheses, you got a big problem, all right? So that's equal. And so the limit as x goes to negative 4. Let's clean up the bottom. This negative distributes, so it's minus 5 and plus x. So 9 minus 5 is 4, and minus gives us plus. and x plus 4 on top, and the 3 plus square root of 5 minus x. Okay, that's great. Looking good. Those cancel. Doesn't matter the order. And now negative 4 is not a problem. So we can now use direct substitution. Remember, the whole goal with all this stuff that we're doing is to get it down so we can use direct substitution. So this is 3 plus the square root of 9, which is 3 plus 3, which is 6. There you have it. Okay. All right, we can factor. We can get rid of that radical by multiplying by the conjugate. What about this thing? Ooh, sine and cosine. Well, this is, we can rewrite it. Let's get it into sines and cosines. So we got tangent. Remember from pre-calc that tangent is sine over cosine? Hope so. And then we got the sine of 4x here. Okay? All right. So we've rewritten this. Okay, and I kind of put them together in one fraction too. So we've got to ask ourselves, where is the problem here? Well, is there a problem? Actually, you know what? I don't think there is a problem. Looks like this problem needs to be rewritten. That's the problem. Okay, so as it is, it's not a problem. 0 is not a problem with tangent. I should have checked that out first, right? Because when you plug in 0 here, you have 1 on the bottom, right? And you have the sine of 3 times 0 and the sine of 3 times 0. Okay, so this is actually just going to be, well, plug in the sine of 0 is 0. Sine of 0, or 4 times 0, is 0. And that's over 1. Okay, so that's 0. Well, let's change a different problem. Okay, let's call this C.2. What if we have the limit as x goes to 0 of cotangent? All right, there we go. Now we got a problem. That should have been what we had, sine of 4x. Okay, that's going to give us trouble. So let's evaluate this one. Different problem. All right. So while we're at it, again, bonus. Okay, let's change that up. So make it a little more interesting. So this is equal to the limit as x goes to 0. Now cotangent is cosine of 3x all over sine of 3x. There we go. Okay, this one you can't just plug in the 0 because it won't work. All right, so we have to kind of work with this a little bit here. Okay, we have to say, what do you wish was under here? All right, now maybe let me go ahead and break this up. Limit as x goes to 0 of, let's say we got cosine 3x over 1 times 1 over sine 3x times sine 4x over 1. Okay, so we have to ask ourselves, what do you wish was up here so that this limit, which should all be in parentheses, can be evaluated? Well, we have a special limit. Our special limit is when the sign on one side or one part of the fraction has an argument that's equal to the top there, okay? So I wish I had a 3x up top, right? We wish we had a 3x. Can I just put a 3x there? Well, I can if I put a 3x on the bottom. And I wish I had a 4x down here. Can we just put a 4x there? Well, if I multiply the top of the fraction by 4x, we can. Okay? So what happens here? Well, let's see, I'm running out of a little room. Well, that's okay. We'll sneak over here. Okay? So what happens is this. We've got as x goes to 0, all right, we have this cosine of 3x is going to, well, it's just going to cosine of 0, which is 1. Okay? And we have this bit right here. What is sine 3x over sine 3x going to? Well, that's going to 1. And what is sine 4x over 4x going to? Well, that's going to 1 also. Okay? So what we have is this, well, let me just put it as 1 over 3x times 1, and then I got this 4x over 1, if you want, times 1. All in all, there's a 4x over 3x, which is 4/3. Okay, there it is. Okay, so we want to use this special limit that is, equivalent to sine of x over x, or as long as these are the same, it works the same. Okay, and we end up with 4/3 in this case. Okay, all right. So a little alternate version, but that's really much more interesting and what we're going for. Okay, a couple more here. What happens here? Well, we want to get rid of that denominator, so we want to multiply by x minus 1 here. Okay. Why x minus 1? Well, that's the common denominator. There's no denominator over here, or it's a 1 if you want. Okay, you could put this over 1. But take the common denominator. Now, there's other approaches, but this approach works pretty slick. And then distribute this. So if we distribute this, we get a new limit. X goes to 3. And on top, I have 2 times x minus 1 minus, and when you multiply x minus 1 times this, it's going to cancel and just leave x plus 1. Watch out. Put that in parentheses. And on bottom, don't multiply that out, because we're trying to make this go away. So if you multiply it, you're just going to have to factor it again. Okay, don't multiply that out. So let's clean up the top. Okay, this is limit as x goes to 3 of distribute, and we get 2x minus 2. Distribute this negative, minus x and minus 1. All over x minus 3, x minus 1. And good news, that top does simplify to x minus 3. And the bottom's still x minus 3 times x minus 1. The problem is the x minus 3, because if you plug in 3, it becomes 0. But that cancels, and maybe we'll leave a 1 behind. And so I'll rewrite it, limit as x goes to 3 of 1 over x minus 1. That's not a problem. Plug in 3, and we get 1 over 3 minus 1, which is 1/2. There you have it. So cancel out the denominator to make when we have a compound fraction, get rid of that denominator so it's a simple fraction, and work from there. Okay, a couple infinity ones here. So how do we find the limit of infinity here? Well, remember that the limit at infinity is only going to really matter about those leading coefficients in a rational function. When we multiply this out, if you were to multiply all this out, it would start with an x cubed, right? And then other stuff that we really don't care about. Because as we're going to infinity, all this other stuff cancels out. And then only the largest degree will remain. So this is equivalent to limit as x goes to infinity of 4x squared over x cubed. Well, that's just, this x squared will cancel with 2 of those. So this is going to limit as x goes to infinity of 4 over x, which once we know there's a high degree on bottom, this whole thing's going to 0, because as this blows up, it's 4 over a gigantic number, and so 0 is the answer. Okay. How about this one? As x goes to negative infinity, well, again, these small terms on top don't matter, and the small term on bottom doesn't matter. Leave the square root around. Don't get rid of that square root yet. Okay, so we've got the square root of 49 x to the 4th all over x squared. And so this is the limit as x goes to negative infinity of 7x squared over x squared. And good news, those just cancel. Doesn't matter if it's positive or negative infinity. And this is 7. All right, that's how that works. Okay. So there we go. Quick recap. We got our techniques. We always got our direct substitution. But if that gives us 0 over 0, an indeterminate form, then we're going to have to factor. There's a possibility. Or if it's got a square root in there, we want to multiply top and bottom by the conjugate. If it's got sine, cosine, or tangent, okay, we want to, well, first try to plug it in like this one hadn't worked. But our little alternate version gave us the problem, and that's where we needed to make it into one of our special trig limits. You got to know there's 2 trig limits. Make sure you know them both. Okay, there's this one, and then there's 1 minus cosine over cos or over x, which is 0. If we have a fraction, a compound fraction, we need to get rid of that denominator, clean it up so that we don't have a compound fraction anymore. Then we should be able to evaluate it. Okay? As we're going to infinity or negative infinity, the small terms don't matter. Rewrite the limit without the small terms in the fraction. Now, by the way, this is only if it's a fraction. If it wasn't a fraction, you can't just cross things out like this, okay? It's only because a fraction is a comparison of the top and the bottom. And so when we're doing this comparison, those small things don't matter in the comparison. So, and a little twist with the square root. So, all right, there's your algebraic techniques. A little bit more, we'll wrap this up. Now for limits on graphs here. So we got our graph, limit as x goes to -3. Well, that's coming to both sides from here. Remember, the limit's looking for the y value 3. And as we go to 2 positive, well, that's going to here. Doesn't matter that it's missing here, by the way. So what is the y value as we go to 2? It's 0. How about -1 from the left? Well, -1 from the left is going to 1. -1 from the right is going to a y value of 2. So what's the limit as we go to -1? Well, this one doesn't exist because they don't agree. Okay? And what about as we go to negative infinity? Well, as we go to negative infinity, this is going to, it's going down forever to negative infinity. Okay? So there's our graphs. Our last topic for this unit will be the intermediate value theorem. So on the intermediate value theorem here, the key is that if we have 2 x values a and b, and they have a continuous function, it's got to be a continuous function, then for any point between f of a and f of b, you pick any number between f of a and f of b, and there has to be a number between a and b, so that f of c is between f of a and f of b. So, but the key is it has to be continuous. So here we got functions f and g that are continuous, and we got a table below, okay, and we've got another function h that's defined like this. So if we want to explain a couple things here using intermediate value theorem. So first we're going to explain why there must be a value c in between 1 and 5 such that f of c is 6.5. How can you be certain of that? Well, we need to point out what we need to find f of 1. Now notice the boundary points are 1 and 5. So we're going to find f of 1 and f of 5. F of 1 is 3 according to the table. F of 5 is 7 according to the table. Is 6.5 in between 3 and 7? Yes, it is. So we can say, since f of x is continuous, we've got to state that. So we got to say it's continuous, and what else? And f of, let's back up here. And f of 1 is smaller than 6.5, which is less than f of 7. Okay, since that's true, then by the intermediate value theorem, there must be C between 1 and 5. So we're just copying that little statement, okay? There must be a C between 1 and 5 such that f of C equals 6.5, okay? So this last little part is just kind of copied from the question itself, okay? Well, what about this? What about if we want to explain that there must be a function, there must be a value w between 1 and 5 such that h of w is 0. Well, what is h of 1? Well, now this gets a little trickier because we've got this definition of h up here. So what I'd really recommend is you write it out. Don't go too far. Don't try to figure anything out. Just put 1 in place of x. So where it says f of x, we're going to make that f of 1. Write it out. Now, figure out what that is working from the inside out. What is f of 1? Well, f of 1 is 3. So this is g of 3 plus 2. What is g of 3? Well, g of 3 is negative 10. So this is negative 10 plus 2, which is negative 8. All right. What about h of the second one, 5? Well, again, write it out. G of f of 5 plus 2. Write out the function with 5 in place of x. Okay. And so, well, what is g of 5? I'm sorry, f of 5. F of 5 is 7. So this is g of 7 plus 2. Well, what is g of 7? Well, g of 7 is this 25 over here. So that's 25 plus 2, which is 27. So we ask ourselves, is 0 between negative 8 and 27? Yes, it is. And so we can say, since h of x is continuous, and by the way, it's continuous because g and f are continuous. G and f are continuous. So because the pieces that make it up are continuous, then h is continuous. So h of x is continuous, and we've got to state that the 0 we're looking for, that y value, is between 27, or we can say h of 5 and h of 1, by intermediate value theorem, and you can abbreviate IVT, okay? And again, now we're just kind of copying, okay? There must be a w between 1 and 5, okay? There must be a w for 1 less than w less than 5, such, just copying that statement, such that h of w equals 0. Okay? Kind of a lot of verbiage there, but again, we are stating the requirements. It's continuous, and it's between, the 0 is between h of 1 and 5. And then again, this little bit here is coming from this statement up here. Okay? Well, that's it. There you go. So there's your review. Hope that helps. Keep working hard. You guys are going to do great.